Paraphrase Enrichment. So let's begin. A brief overview of what I will be going through today. It will start with an introduction on the problem statement and what led to the title of the paper, some background on the datasets that are being used, the metrics that are being used. Third, we will go into our proposed approach. We will then move on to the results and analysis and end with conclusion and future work. So let's start with the introduction. So recently there was the shared task, which was held as a part of SemEval 2024. SemEval corresponds to semantic evaluation, which is a workshop held with the NACL every year. So this year, shared task 4 actually introduced on focusing on identifying persuasion techniques in memes, thereby highlighting their role in disinformation. So the task 4 involved two subtasks, in which the first subtask involved analyzing textual content of memes to detect 20 hierarchical persuasion techniques, whereas subtasks 2 and 3 examined multimodal memes, which is by considering both the textual and visual elements. Today, I am going to present our approach that we use for our participation to the subtask 1, which focused only on the text of the memes, and also some further analysis that we did with the dataset after the shared task. To give a brief overview of our approach, we fine-tuned 3 individual language models and then ensemble it using a mean-based strategy. And in addition to this, we also generate paraphrases as a part of our data augmentation technique to further improve our scores. A little background on what the task deals with and what kind of data sets we used. So the subtask 1, the main goal of the subtask was for our system to categorize the textual content of memes into one or several persuasion techniques. And as you can see, the techniques over here are organized in a hierarchy as shown on the left. So there are a total of 20 techniques where each technique is identified by a leaf node. And the hierarchy also has other nodes which correspond to the main category of how these techniques are classified. Now, since there is a presence of an hierarchy, the task was viewed as a hierarchical multi-label classification task, which means that instead of using the vanilla precision, recall, and F-score measures, we used hierarchical precision, hierarchical recall, and subsequently the hierarchical F-score. So these are the formulas that were used to calculate the precision, recall, and F-scores. A little more on what PI and TI actually represent over here. PI is the set of consisting of the most specific class predicted for a test instance I and all of its ancestor classes. Whereas TI is the set consisting of the true specific classes of test example I and all of its ancestor classes. So we calculate hierarchical precision as a sum over all instances of the intersection of PI and TI divided by the sum over all instances of PI. Whereas recall, alternatively, we calculate it as the sum over all instances of the intersection of PI and TI divided by the sum over all instances of all the true labels for all I instances. And the F-score is then calculated by 2 times the hierarchical precision and recall over the sum of hierarchical precision, and hierarchical recall. Now, coming on to the data sets that were given to us by the organizers. So the training set consisted of 7,000 samples in just English. The validation set consisted of 500 samples in English. The development set, which was used as to submit on the leaderboard during the task, consisted of 1,000 samples in English. But during the test time, there were 3 new languages introduced, mainly Bulgarian, North Macedonian, and Arabic, in addition to the English test set that was already present. So a sample instance that could be found in any of the training, validation, development, or the test set is as given as below. So each instance has an ID along with the text, which is found in a mean, and the labels that are associated with the text. So here we see the text to be, "Don't expect a broken government to fix itself." And the persuasion techniques or labels that are associated with this text are loaded language, slogans, and name calling or labeling. Here we see the distribution of instances for each persuasion technique in the training set. And as we see, there's a clear imbalance in the number of instances for each technique. Specifically, some techniques such as loaded language and smears have large number of instances, whereas techniques such as strawman and red herring are very severely underrepresented. Now, coming to the proposed approach, a brief overview of the system that we are going to use. As I told before, our methodology is mainly focused on fine-tuning 3 distinct pre-trained models, mainly BERT, XLM-RoBERTa, and mBERT on our augmented datasets. Now, despite the hierarchical organization of the problem, we opted for predicting solely the technique names and not their ancestor nodes, which means we just opted to predict the leaf nodes of the hierarchy, and we ignored predicting the ancestor nodes. So this is a diagram of how our system has been implemented. It starts with the input, which is the paraphrase augmented data, which then goes through a vanilla pre-processing step, which is common in all NLP tasks. Then the output of the pre-processing module goes into 3 different models, namely BERT-based uncased, XLM-RoBERTa base, and mBERT. And now the outputs from these 3 models are again passed through 3 feed-forward layers. And the outputs of these 3 feed-forward layers are then ensembled using a mean ensembling strategy. Then these ensemble predictions are passed through another final MLP classifier layer, which would finally help us identify the most likely persuasion technique or techniques associated with that text. Now, to deal with the multi-label classification part of it, we implemented thresholding, which determines which techniques actually qualify to be a part of the output label set. For this, we experimented with the custom threshold values for each technique, mainly ranging from 0.01 to 0.7. We also then selected optimal threshold values for each class based on the performance on the validation set that was given to us. We then applied these thresholds to the scores obtained after the feed-forward layer, and then used these logics and passed them to a sigmoid function. Coming on to the data augmentation, which is the second most important part of our system. So as we saw, there was a clear imbalance or lack of data for most persuasion techniques, as they were severely underrepresented. So to mitigate the lack of data, we took advantage of two data augmentation strategies. The first one being using an external data set, and the second one being to automatically generate paraphrases. Let's talk about the first strategy now. So in order to use an external data set, we actually use the technique classification dataset from SemEval 2020 task 11. A little bit more on this dataset. This dataset actually contains spans of text labeled with multiple persuasion techniques, which were not in respect or aligned with the techniques that were given this year. So the techniques had to undergo a pre-processing. I'm sorry, the instances from the SemEval 2020 dataset had to undergo some sort of pre-processing so that it would be aligned with the SemEval 2024 dataset. Now, given an external dataset, we hypothesized two approaches that we could leverage to use this modified dataset. The first approach would be to pre-train our models on the 2020 dataset and then fine-tune it on the 2024 training set. The second approach would be to combine both datasets and fine-tune models on this combined dataset. We went with the latter approach because we hypothesized that this would enable the model to adapt to and grasp nuanced linguistic patterns across different genres. It's different genres because the SemEval 2020 dataset focused in the news genre, whereas the SemEval 2024 dataset focused in the meme genre. So now we refer to this combined data set as Comp14K, as it contains nearly 14,000 instances. So we would use this name in order to further address this data set in the rest of the presentation. Second thing, or the second method that we used to address the lack of data was paraphrasing. So we generated a set of paraphrase data sets mainly with n equal to 1 and n equal to 3. So I will tell more about it as I explain further. So we saw despite having almost doubled each class with the use of 2020 dataset, some classes were still severely underrepresented. So to address this, we took advantage of a large language model to generate paraphrases for each training instance, and then label these paraphrases with the same set of labels as the original instance. So our intuition was twofold. First, generating paraphrases would actually expose our models to a more extensive set of examples for each technique, and thus improving its ability to discern subtle nuances. The second being paraphrasing sentences also unveils hidden semantics, which are very necessary to for the model in identifying persuasion techniques based on the linguistic choices or how the sentences are actually phrased. So thus to generate paraphrases, we leverage GPT 3.5 Turbo or ChatGPT 3.5 with the setting of the temperature to 0.7. Next, we generated n paraphrases for each instance in the Comp14K dataset. And we experimented with n equal to 1, which is basically generating one paraphrase for each instance in the Comp14K dataset, and with n equal to 3, which is generating three paraphrases for each instance in the Comp14K dataset. This led to two additional datasets, which are called as para n1 and para n3. We see that the overall hierarchical F-score on the validation set of 500 instances actually increased while using these datasets. I will show you the table of scores when I move on to the results and analysis section. And we also saw that training with n equal to 3 performs better than just training with n equal to 1. That means more the paraphrase is generated, the better the model would perform. So then we also dealt into a per class analysis for each technique to see if generating paraphrases actually benefits all the classes, or does it benefit only a few classes. So we saw that not all classes benefited from the increased support. For example, the persuasion technique bandwagon had an increase in its F-score from 0.17 to 0.29, while the technique repetition had a decrease in its F-score from 0.56 to 0.31. Thus, we identified classes only with an improvement in F-score greater than 0.03 when using the para N3 dataset compared to the original COMP14K dataset. Thus, we identified 8 techniques or 8 classes which showed an increase in their F-scores. So these 8 techniques form the basis for our subsequent strategy. So here you can see the graph which shows the 8 techniques that actually had an increase in their F-scores. We see that bandwagon has the maximum increase with a delta of 0.12, whereas slogans and whataboutism has the minimum increase with a delta of 0.04. So the blue bars over here correspond to the F1 scores that we got after training on the COMP14K dataset, whereas the orange bars represent the F1 scores we got after training on the Para N3 dataset. Just to reiterate, the Para N3 dataset was actually generated by generating 3 paraphrases for each instance in the COMP14K dataset. Thus, since we identified 8 new techniques, we generated a new augmented dataset by generating 10 paraphrases, which is an increased number of paraphrases only for the 8 techniques that benefited from paraphrasing. We call this set of 8 techniques as set B. Now, for each instance in the COMP14K labeled with techniques T, we generated 10 paraphrases for each technique Ti in B, labeling them with all techniques from the set intersection of the set T and B. So this led to this newly created dataset called ParaBenef, which contained 54K instances. It is called ParaBenef because it mainly contains paraphrases for only those techniques that were actually benefited by generating paraphrases. So now the figure here below shows the distribution of instances across all the para data sets that we had generated. So we see that the gray bar over here actually corresponds to the original training set. The gray plus pink corresponds to the COMP14K data set, whereas the gray plus pink plus the violet corresponds to our ParaBenef dataset. So as you can see, the ParaBenef dataset is only categorized by these 8 techniques over here. So you can see the violet bars are only present 8 times as opposed to the pink bars, which are present for all techniques. So we can still see that there is still not a good balance that has been achieved. We might have actually helped or have had more instances for underrepresented classes, but still, while looking overall, the imbalance is still present. So since thus we also needed to address the imbalance issues, and therefore our next data set tried to address this issue as well. So to address the dataset imbalance, we use the same paraphrase generation strategy that we used before. Specifically, we generate paraphrases only for the underrepresented classes in the initial training dataset. So so over here you see that techniques like bandwagon or red red herring or strawman, reducto, and Hitlerium are severely underrepresented. So I'm sorry. So thus, our paraphrasing generation strategy actually addresses on augmenting these techniques only. So we aim to match the instance count of three most frequent techniques, which are loaded language, name calling, and smears. And to do this, we generated batches of 5 paraphrases for each of the other techniques to reach around 1,500 instances. And this newly created balanced dataset is called Paraval, which contains 49K instances. Here we see the instances per label distribution for the Paraval dataset. We see that the dataset is now almost balanced. We can call it a balanced dataset, except for the 2 peaks you see over here. But those don't matter so much because the difference in the instances was a couple of hundred or 200. And now coming to the results and analysis that we got after running our models on all the data sets that we had. So here is the table which shows the hierarchical F1 scores of all our models when trained on the different English language data sets, and also on the validation set and the development set. So we see that the original training set gave us very less scores with 0.45 on validation and 0.46 on development. Once we combined it with the SemEval 2020 dataset, we found an increase in score, which was observed both in validation and in the development set. And after that, when we generated one paraphrase for each instance in the comp14K, we again saw an increase in score in the validation set, but not so much on the development set. So this inspired us to check if more paraphrases would actually improve scores, which led us to generating 3 paraphrases for each instance in this data set. And we see that we also get an improvement in the validation set and also in the development set. So after this, again, we wanted to see if all classes were actually benefited by increasing the number of paraphrases. Thus, we then generated paraphrases only for the 8 classes which we identified as benefited. And we see that there is actually a decrease in the performance. I will go on to more analysis on why this happened in the next section. And finally, we see that the balanced data set actually outperforms all the other data sets. We see that we get a very significant improvement on the validation set and also on the development set. So for the official submission to the SemEval, our model was based on an ensemble model, which was trained on the union of para and 3 dataset and the development set, which in total gave us 53K samples. During the submission or the time of submission, we had still not generated the Parabal dataset, which actually outperformed the Para N3 dataset as we saw in the previous slide. So since the Parabal dataset was not created at the time of submission, it was more done as a post-task work. We did not use that dataset. Now, as I told before, the test set included 1,500 samples for English, 426 for Bulgarian, and 259 for North Macedonian, and 100 for Arabic. So during the testing phase, we automatically translated all the other language datasets into English by using the Deep Translator framework. So I'm going to show the official results of the performance of our system, which is along with the baseline given by the organizers and the best score which was obtained in the task. So we see that our system performed better than baseline in all languages, significantly, except Arabic, where the improvement was not that much. But I would like to make a note here that not all the teams that participated in the shed task actually surpassed the baseline for Arabic. And our team was one of the very few teams which passed the baseline for all the languages. We also see that uh, using the Parabal dataset, we have a significant increase in the score for English language as compared to the baseline. So again, results using the balanced training dataset, which is Parabal, showed an improvement in score compared to Para N3 uh, with an increase of 0.05. So this actually highlighted the importance of balancing the dataset and paraphrasing based on the original text distribution. We also see that para N3, although it has a higher number of instances, it might have included paraphrases from different genres, which is memes and news. And this may have actually affected the performance of the model. And thus, it's not always such that a larger data set may also give to a better score. But interestingly, the performance enhancement observed with the Parabel data set in English does not translate to the improved zero-shot classification on new languages. So we see that on new languages, the Para N3 dataset actually performs better than the Parabel dataset. And we think that a reason for this might be that there could have been possibly some introduction of noise when we had automatically translated on from the other languages to English. And it was more significantly less in Arabic. And I feel that when you translate other languages to English, you lose a lot of context. And losing a lot of context would also mean losing important semantic structures, which which might have caused it to perform lesser. So in conclusion, we utilized the ensemble model incorporating 3 fine-tuned language models for hierarchical multi-label detection of persuasion techniques. Our system demonstrated outperformance of the baseline across all languages, thus highlighting the effectiveness of our approach. It also emphasized the critical role of dataset balancing and paraphrasing techniques, because it does not always mean that a larger dataset might always lead to better scores. For some languages, it might be the case, but a balanced dataset, even with a lesser number of instances, actually can perform better than their unbalanced counterparts, which was shown by our results. And we also identified that since we combined the SemEval 2020 dataset, which was from a different genre, into the current meme genre, this might have also indirectly introduced some significant noise. And this highlights the importance of the measures that we need to take when we curate these kinds of datasets. As a part of future work, we would like to implement hierarchical predictions, that is basically make use of the hierarchy by potentially predicting second level nodes, which would or would not even improve our performances. Next thing would be to explore the integration of in conjunction with the language-specific datasets. What I mean by this is, instead of just translating the datasets from other languages to English, we could use language-specific models, which could be pre-trained on those particular languages and used during the testing time for a zero-shot performance. A next technique could be to use